In this video, we are going to show you how you can build an AI/ML-based card fraud detection solution on AWS. In this use case, the card payment authorization application is running on ZOS mainframe system and using static business rules to approve or decline. The legacy application is enhanced to make a real-time call to AWS to get a fraud score generated by Amazon Fraud Detection Service or any other AI/ML model built using SageMaker. The model is trained with attributes, such as customer purchase history, for example number of purchases in last 48 hours, and merchant sales history, for example reported frauds in last 24 hours. During inference of the score, same attributes are passed to the model to generate optimal score. Let us review the solution architecture. When a customer swipes a card at terminal, or makes an online purchase, the bank will receive the authorization request on the mainframe system. The application will make a real-time call to AWS. The process running on AWS will get the customer and merchant history details from relational database and provide to the AI/ML scoring model running on, say, Amazon Fraud Detector Service. The model will return a score. Higher score will indicate potential fraudulent transaction. The mainframe application, combining with the other business rule, will make a decision to approve or decline. The transaction detail is inserted on mainframe database, either VSAM, DB2 or IMS. The record will be captured and replicated to AWS near real-time using Precisely. The Precisely publisher agent is running on mainframe, and the apply agent is running on an Amazon EC2 instance. The apply agent converts raw database logs, received from publisher agent, to JSON format using the copybook, and publishes the messages to Amazon Managed Streaming for Kafka or MSK. Several service will consume the message from MSK. A Kafka Connect process can pull the messages from MSK and write to RDS database. The history details are read from same database during the scoring process. MSK will stream the messages to Amazon S3 using no-code integration with Firehose. The data on S3 will be used offline to train the AI/ML models along with other internal or external data sources. For analytics and business intelligence, the messages from MSK can be pulled to Amazon Redshift. Business users can run query against the database using natural language. Similarly, other integration may be built using Amazon Event Bridge Pipe to stream data to services like Amazon SNS or Pinpoint for notification and alerting. In this demonstration, there are several AWS resources created. Some of them are pre-built using CloudFormation template. This includes VPC, subnets, IAM roles, AWS Key Management Service, etc. On AWS console, we can see there is a VPC created with 3 subnets. Private link endpoints are created for access to serverless services, such as Secret Manager, STS, Event Bridge Pipes, etc. A MSK cluster is defined in the VPC, with 3 brokers and 3 different subnets. Both IAM and SASL, password-based authentication is enabled. The credentials are stored in Secret Manager. The Bootstrap server's details for both IAM and SASL authentication types are available in client information. A RDS Postgres database instance with DB name as Card Payments Fraud. A Lambda function is created to pull the messages from MSK and insert RDS Postgres database. The function will be running in the same VPC. The environment variables are set for RDS database connection details. A SNS topic, messages from MSK will be streamed to SNS using an Event Bridge Pipe. The SNS topic is configured to send email notification. First, we are going to obtain the mainframe data replication software from Marketplace. From AWS console, search for Marketplace. Click Discover Products. Type AWS Mainframe Migration with Precisely on search bar. Click on Data Replication for IBM ZOS. Then click Continue to Subscribe button. Follow the instructions to complete subscription. Next, we are going to set up the Amazon EC2 instance. Once you have completed the subscription, come back to AWS Marketplace console and click Manage Subscriptions. Then, click Launch New Instance. Click Continue to launch through EC2. Provide a name for the EC2 instance. Scroll down to Network Settings, and click Edit. Select the VPC created for this solution. Select one of the subnet. Click on Select Existing Security Group, and from the drop-down on Common Security Group select the security group created for the solution. Expand the advanced details and click Existing IAM role and select Instance Profile created by CloudFormation. Paste the script in the User Data text box. The script first installs the required software such as Librd Kafka, PostgreSQL Client, etc. Then it creates a Kafka folder, downloads and extracts the Java Kafka libraries. Inside the Kafka libs folder downloads the MSK IAM jar file. It creates an IAM authentication client properties file. The jar and the properties file are used by the JavaScripts. Runs the Kafka topic script to create the Kafka topic. Precisely Publisher will publish the records to this topic. Then, runs the Kafka consumer group script to create a consumer group to be used later by the Evenbridge pipe. MSK broker details have to be passed as one of the parameter for the scripts. Next, it creates a Precisely folder and then the SASL producer configuration file for Precisely. Sets the path variable to include Precisely bin directory and runs the school keygen command to create the private and public key file for Precisely. The content of the public key file has to be copied to Mainframe and added in key file for daemon for authentication. Click Launch Instance to launch a new EC2 instance with Precisely software installed. Next, click on the instance ID to open the details page for the EC2 created. Click the Connect button. Type EC2 user for username. Then click Connect. This will open the EC2 command line. The EC2 user data script created the public-private key files for Precisely. The .nacl directory contains the public key file to be copied to Mainframe. The software agent folder contains software components to be installed on Mainframe as zip file. A system administrator access is required to install the software. Log into the Mainframe. In this use case we considered the card payments authorization history is stored in a VSAM database. The screen shows the COBOL copybook used to define the layout of the message. The Precisely software is already installed. An UI is available using the ISPF panel to perform admin works. The daemon process in the publisher is already created and started as a batch job. In this demonstration the daemon job is running on port 9050. DD name sqdauth refers the keys file. The content of the public key file created within the EC2 instance is pasted in this file, and will be used to authenticate the apply engine when connection request is made. Here's the publisher job. From the ISPF panel for Precisely, select option 3. VSM to MSK is the name of the publisher engine, and the configuration is stored in .cab mentioned. The screen shows the different stats such as records captured, records published. The source log stream shows the log stream name configured to stage the database changes. In our scenario, the log stream is a VSAM base file, but in production, coupling facility base log stream is recommended. One source object is configured, which is identified by VSAM pure C. This will capture the logs from the card payments authorization VSAM file. Switch back to EC2 command prompt. We will create the RDS Postgres table. Connect to the RDS database using the PSQL command. Then run the create table command. The table columns corresponds to the fields in the VSAM copybook. Run a select query to validate the table. Next, create a CPY subfolder inside Precisely folder. Create a file named card_payments, and paste the COBOL copybook layout. Save the copybook file. Create the apply engine script file, named script.sqd. The script has the job name VSAM to MSK as identifier. The description section refers to metadata, referring to the COBOL copybook location. VSAM perk is the name of source object identifier set by publisher. Source data store points to mainframe IP address and port for daemon on mainframe. VSM to MSK is the publisher name. VSAM CDC is data source type. Target data store points to topic name of the MSK. Messages will be distributed to Kafka partitions using key. JSON is the record format. Both source and target data source use card_payment_src to describe the message metadata. The script used the replicate function to convert raw EBCDIC log to JSON format with key fields from copybook. Next, we are going to set up the MSK S3 delivery via Firehose and integration with SNS via EventBridge pipe. MSK provides no-code integration with various AWS services. On the MSK S3 Delivery tab, click Create Firehose Stream. Some of the details are pre-populated, such as source, destination, MSK cluster. Paste the topic name. Enter a name for the stream. Select the S3 bucket created by CloudFormation template. Add prefixes. Click Create Firehose Stream to create. Once the creation is complete, you will see the status as active. Next, click Integration tab and then click Connect Amazon MSK cluster to pipe. Enter a pipe name. Paste the topic name and the consumer group created earlier. For demonstration, we are not adding any filtering or enrichment. On the target page, click in Target Service drop-down. You can see the different services you can integrate with. Select SNS, then the topic. Expand Target Input Transformer. On the sample event, select MSK. Click on the value to select the field for output. Click Create Pipe to create the EventBridge pipe. Once successfully created, the status will show as running. Now, let's start the Apply engine and insert some record in the VSAM database. On the EC2 command prompt, start the Apply engine using the sqdeng command. The process displays valuable information about the data sources and message layouts. It's connected to Publisher engine on Mainframe and waiting for data now. Switch to Mainframe. This PS file contains records that will be inserted to the VSAM database. The records map to the layout of the copybook we saw earlier. In this demonstration, we will use the precisely batch differ functionality to replicate data. Online VSAM, or DB2 IMS, follow the same capture-publisher architecture, with some differences in setup and configurations. We are going to use the job to copy the PS file to the current VSAM and then run the sqddfcdc utility. The utility compares the base and current files and updates the change records in the log stream. Submit the job. Switching to the ISPF panel, we see the engine is connected now. The capture and publish record counts have gone up. EC2 command prompt also shows records ingested. Let's switch to another terminal, and let's run the select query on RDS Postgres again. We see the records in the table. The metrics on Lambda console shows the invocations. It picked up the messages from MSK and inserted them to RDS. Let's look at the other data pipelines created from MSK. On S3 console, let's navigate to Data folder, and then to the subfolders. Select one object and click Query with S3 Select. On the page, select JSON as input and output format. Then, run SQL query. We see the JSON message that was published to MSK by precisely apply agent. The change operation is an insert in this case. You will denote an update and delete operation. After image contains the new values of the key fields corresponding to copybook fields and their respective values. An update database operation will have both before and after image. The objects stored in S3 will be aggregated and used offline to train and update the AI/ML models. The EventBridge pipe also consumed the messages and sent email notification with the JSON message as body. Here's a sample email. Now, let's experiment how we can use generative SQL from Redshift to query using natural language. On the Redshift console page, click on Query Data. Click on plus sign and select Notebook. Select the cluster. Run SQL to create schema directly from the MSK topic. And then a materialized view with the data from the topic. Then, click on Generative SQL. A chatbot window is opened on right-hand side. Type in plain language, for example, show top 5 states by purchase. Amazon Q backed by large language model or LLM generates the SQL query to be executed. Click Add to Notebook and then click Run. We see the SQL results. Let's try something little complex. Let's ask show top 5 merchants with highest single purchase. Ask to include state of purchase and output. Also, ask to show the purchase amount in currency format. Using generative AI, Redshift is able to understand the request written in natural language, search the database and generate the SQL. You can do a lot more, ask complex business insight on the data. Here's the result. In case you are looking for the code sample to build the fraud detection section, check the sample code in GitHub. Thanks for watching.